Hello everyone, my name is Tomi Karppinen and I work with Fourier transform spectrometers at the Arctic Space Center of Finnish Meteorological Institute. Here is a wide overview of the Tähtelä area in Sodankylä, which is home for both the Sodankylä Geophysical Observatory and the Arctic Space Center of Finnish Meteorological Institute. At the Space Center we have remote sensing on a wide range of wavelengths and for wide range of applications. For example, a bit deeper in the forest we have a 50-meter high tower with several remote sensing instruments for snow and ground moisture parameterization. These use the microwaves and short radio waves emitted by ground and scattered by snow to gather information about soil freeze and snow water equivalent. At sounding station platform we have instruments measuring from visible to near infrared wavelengths to gather information on aerosols, and then instruments measuring UV radiation that can be used to retrieve ozone columns. It is also the home of the balloon-borne measurements. Rest of the presentation considers this area. In this area we have side by side two Fourier transform spectrometers, Bruker IFS125 and EM27 Sun. Bruker IFS125 resides on the second floor of what we call the Moomin house. There is a tracker on the roof to guide the solar light in. The instrument itself takes a considerable amount of space in the room upstairs. EM27 is more portable instrument, even though it is a bit heavy to be carried by only one person. It is protected from harsh weather by a box with a rotating cone on top to allow measurements when the sun is shining and to cover the instrument when it is raining or snowing. For both instruments, the measurement principle is the same. They measure the spectrum of direct solar light, and from the absorption features in the spectrum, several gas concentrations can be retrieved. So, how do these instruments actually work? This is the insides of the IFS125. Let's start from the box on the lower right. So the sunlight enters the instrument here, and then it is focused on the entrance aperture. Nowadays there is a camera installed here to monitor the location of the sun's image, which is the bright circle, on top of the entrance aperture, which is the small dark circle. The camera information is communicated to the solar tracker via a software to command the tracker and keep the circles perfectly aligned. The wavelength separation is done by the interferometer consisting of parts marked with 1, 2, and 3. When light reaches the beam splitter, half of the light continues towards the moving mirror and half reflects towards the static mirror. After reflecting back from these mirrors, the light beams are recombined and guided towards the detectors, and the intensity is recorded. Here is a simple example of the interferometer operation. Let's take only one wavelength. We can consider that as a laser beam, basically. So the image on the left shows the instrument insides. The figure on the right shows the waves coming from the static mirror with the solid blue line and the wave coming from the moving mirror with dashed orange line. The black line is the superposition of those. The power within the superposition wave will be measured at the detector. When the moving mirror and the static mirror are at the same distance from the beam splitter, the recombining waves will constructively interfere and the intensity of the light will be the same as it was before the splitting. When the moving mirror starts to move further from the beam splitter, the recombining waves are not in the same phase anymore, and the intensity of the combined beams is not the same. Whenever the distance difference of the light path, the so-called optical path difference, is the multiple of the wavelength, there will be a constructive interference. And whenever the distance is an odd multiple of half of the wavelength, there will be a complete destructive interference. The intensity measured during the whole moving process of the mirror will be a replicate of the ingoing wave. With a continuous spectrum, the shape of the interferogram is more complex. However, with the Fourier transform, the interferogram can be transformed into a spectrum. The figure on the right shows the different wave number ranges covered by the different detectors. Now, the difference between the IFS125 and the smaller EM27 is the maximum optical path difference they can achieve. In EM27, the optical path difference is created by rotating the mirrors around the beam splitter, creating a maximum optical path difference of 1.8 centimeters. This is much shorter than the 45 centimeters usually used in the IFS125 measurements. The maximum optical path difference translates to wave number resolution in the spectrum, so the EM27 cannot see as sharp features as the IFS125. This is even more apparent in the spectral ranges where there are a lot of features really close to each other. Let's then look at how the spectrum is turned to a gas concentration. Gases at different ambient conditions create different absorption shapes. At low temperature and low pressure, typical for higher altitudes in the atmosphere, the absorption features are narrower. At higher temperature and pressure, the features broaden due to collisions and thermal movement. The features seen in measured spectrum is a combination of different shapes from different altitudes. That's why we need to have prior information on the shape of the altitude profile of the retrieved gas. This can be, for example, from balloon-borne sampling of the atmosphere or from satellites measuring in limb viewing geometry. Usually the retrieval is made by modeling a spectrum using a prior profile shape and multiplying that profile to find the best match between the modeled and the measured spectrum. However, in the high-resolution measurements, there is enough information to try to manipulate also the shape of the prior gas profile. In the method by Tukiainen et al., the prior profile is manipulated using the highest singular vectors derived from prior covariance. The objective is to find the best coefficients for the singular vectors to match the modeled and the measured spectrum. And then next up there is a small simplified demo of 3-layered retrieval of methane concentrations.
Finally, I wanted to show you this methane retrieval demo created by Antti Mikkonen. On the left you can see a measured transmittance, spectra, and a calculated one. And the calculated one is at the moment 1 throughout because there is no methane yet. On the right you can see the residual, so the difference between the measured and calculated one. So just to show you, if you plug some methane in the stratosphere, you create these sharp features, and at the tropopause altitudes the features are a bit wider, and then in the troposphere you create these wider features. So you can try to find the best fit between the calculated and the measured one, and you can play around with it in this address retrieval demo.fibonacci-vene.xyz.